All right, let's talk about some common op-amp values, and then we will go and look at the ideal op-amp technique. Okay. An actual op-amp does not have, it is not ideal. A real op-amp has inverting or has input resistance Ri, and it has non-infinite input impedance Ri. It has non-zero output impedance Ro. And here we're showing the schematic symbol. Notice that VP is drawn on the bottom here. Let me do this in red just to match my notes. This is VP as drawn on the bottom here. VN is drawn here, that's V1. And VD is the differential voltage. We call that the differential input voltage. And so it turns out that an amplifier, we call it VD, the input is the differential voltage, because the amplifier itself gives out the dependent voltage source inside of the op-amp, gives out a voltage that is A times the differential voltage VD. So VD is equal to VP minus VN. All right, the output voltage is then A times VD, and VD is that difference, V positive, V plus minus V negative, Vn. Okay, here's some, we've already sort of shown the pins and those kinds of things on the last slide. Let's talk about some typical values for a real op-amp. The gain for an op-amp, again, this is the open circuit gain. This is the open circuit gain, or the unloaded gain, is commonly in the range of around, that would be a 10 to the 5, that'd be 100,000 volts per volt, up to 10 to the 8, I think that's 100 million volts per volt. Okay, those are very high gains. We'll talk about why you need such a high gain a little bit. And how about the input impedance? The input impedance, while not infinite, we can get pretty good. At least a mega ohm, 10 to the 6 ohms, and oftentimes much, much higher, even up to, in some op-amps, a few tera ohms, which 10 to the 13, that'd be 10 tera ohms. Okay, how about the output impedance? And I'm saying impedance now instead of resistance. I'm going to continue to start to use that word instead of resistance for two reasons. One, we're going to start to talk about AC resistance, in other words, impedance, as we start to move into the next segments of the course in the coming weeks. And so I want us to get more familiar with the idea of impedance. The units of impedance are ohms. It's generally a term just used. Now, when you're talking about amplifiers, a lot of times amplifiers are used with AC signals. So they aren't DC signals driving them. And so the resistances aren't just resistances. There are frequency dependent resistances in the circuit. Those are made by inductors and capacitors. And we then start to talk in more general terms about the impedance, the input impedance of an amplifier, the output impedance of an amplifier. So this is a kind of semantics or vocabulary thing used in electronics. And I'd like for us to be conversant, for you guys to become more conversant in those ways. So we'll use the term impedance, which is sort of generally used in electronics discussion. Okay, so the actual amplifier is not ideal. It doesn't have infinite input impedance. It doesn't have zero output impedance. But can we get close to that? And we can through some assumptions. Let's make a couple of assumptions. Let's assume that the input, or that the open circuit gain is infinite. Okay, let's assume that the input impedance Ri is infinite, and let's assume that the output impedance Ro is 0. Okay, if we're doing that, and as we saw on the last slide, A times, or the output voltage V out is equal to A times VD, which is A times what VD, the differential voltage, is VP minus VN. It's the difference between the inverting and non-inverting terminals. Then we could actually rewrite this and show that V out divided by A is equal to VP minus VN. All right, all we did was just divide both sides of that expression by A. Now, if A is infinite, if A is infinite, then that means this whole term, the only way for this solution to be mathematically consistent is that that whole term has to be 0. VP minus VN is 0. And if that's true, then what we can say is that VP, the non-inverting terminal, is equal to, must be equal to VN, the inverting terminal. And that is, in fact, the main result here, that the differential voltage VD is 0 and VP is equal to VN. In other words, the op amp, the input terminals of an op amp, so VD, the differential voltage here, oh, whoops, I drew that the wrong polarity here. It's positive down there, negative up there, right? VD is 0. In other words, what that means then is whatever VN is and whatever VP is, VP has to equal VN and VN has to equal VP if the differential voltage between them is 0. Okay, now if it's 0 and the input impedance is infinite, in other words, there is in here, there's not a little resistor in here. In fact, it's an open circuit. Then that means that there's no current flowing in here. IN is 0. And in fact, there's also no current flowing in or out of this terminal as well. There's 0 amps of current flowing in and out of the negative line as well. So it's kind of strange, but the input terminals of an op amp then both model a short circuit where the voltage is 0 between the 2 points and an open circuit. It's kind of a weird way to think about it, but that is that is sort of part of the outcome. So let's then talk about this ideal op amp technique. So the ideal op amp technique is basically assuming these things. We're going to assume the gain is infinite. We're going to assume the input impedance is infinite and the output impedance is 0.